So welcome, my name is Chad Ostrander. I am the Secretary Treasurer for the Dallas Greater Section of TechSite. It is my honor to moderate the presentation today. Our speaker today is Dr. Zong Tian. He joined the University of Nevada, Reno in 2004 and is currently a professor and director for the Center of Advanced Transportation Education and Research at UNR. He obtained his PhD from Texas A&M University, and his professional career has included positions at Texas Transportation Institute and Kittleson and Associates, Inc. Dr. Tian is active in various professional organizations, including two major TRB committees, the Traffic Signal Systems Committee and the Highway Capacity and Quality of Service Committee. He is currently the topic area manager for Area C of the World Conference on Transportation Research Society, overseeing 4 special interest groups in the area of transportation systems. His specialty is in traffic signal systems and operations, highway capacity, and integrated freeway and arterial operations. Please help me welcome Dr. Tian.
Okay.
Dr.
Can you see my screen?
Yes, we can.
Sounds good. All right. Thank you, Chad, for the introduction, and also thank everybody for giving me this opportunity to talk to you about some signal timing related technology tools. Chad already made a good introduction, so I don't need to repeat the information about myself, but I just highlighted that's where I attended school at Texas A&M, where I got my PhD. So I'm pretty sure there must be some Aggies among the audience. But I do want to brag a little bit about our students here, since this is an IT meeting. So we have a very active IT student chapter here. So I just want to highlight the kind of student awards we have received for the past 10 years or so. At the international level, so we have won twice for the Best Student Paper Award, and also the award from ITS America, first prize. At the regional level, we used to belong to IT District 6. Now we belong to the mountain section. It's a new section. So we participate in student paper competitions almost every year. So we have won 6 times the best student paper from IT District 6, and numerous awards from IT Intermountain section. And our chapter is in Nevada, so Las Vegas Fall Conference. So this is a table that highlights all the students' awards for between 2007 and 2020 in District 6. So I highlighted those, won by our students here, including twice the international level, Dan Fambro Best Student Paper Awards. With that, so I'm going to get into the actual presentation. So what I'm going to talk about, in fact, I'm going to first emphasize, I call it critical aspects or critical issues, challenges, for in the signal timing field. So in fact, I'm not going to talk about adaptive system. Adaptive system definitely is emerging technology, but I'm not really going to talk about adaptive system. I'm going to focus really on the conventional coordination timing, because still more than 95% of our signals are under this type of control, the conventional time of day signal timing coordination. So these are the 4 issues that I'm going to emphasize. I'm going to talk briefly of each of them, and then I will just show some technology tools. How can we use those technologies to address these challenges, these critical issues? The 4 things, I call it the mode. So managing signal timing coordination data, optimizing timing plans with minimum data, diagnosing timing errors in the field, and also evaluating. How do you evaluate the quality of a signal coordination? So the first, managing. Here I mean managing means, having all your signal coordination timing data in a central place so that you can easily build a timing plan, modify it if you want, and also quickly assess the quality of the timing plan, such as looking at a time space diagram of a specific segment of a roadway. Well, if you look at the current practice, I think I know very well. I work with many different agencies. The first question I ask them, do you have a file where you have all your signal timing data? I'm talking about the coordination timing data. So in most cases, Synchro is the most popular software every agency, every firm is using. But in most cases, they have Synchro files, but usually many files. Okay, they created many files, and they even don't know whether those files, the timing in the Synchro files really match what's in the field, right? That's what I'm talking about. So very few agencies actually, they have a place where they store all their signal timing data. So somebody may say, yeah, we have the central system. But you understand the central system, yes, you have all your timing there, but it's really not for managing optimization, those type of things. Central system is mainly for monitoring. If I request the timing data, so they still need to get into the central system, extract those timing sheets, the raw timing sheets, right? So it's really not convenient. So I'm talking about you can have everything, have everything in one place, in one file, and you can have multiple timing plans, such as the intersection here. You can store as many as timing plans you wish. And then you can pick a certain segment of the roadway to easily view the time space diagram, for example, because there's an indication of the quality of a progression. Right? So that's what I'm talking about. So I will just stop there. So there is a tool to actually do this. Later, if you want to know more details, certainly you can contact me. The second part I want to talk about is optimization. So traditionally, right, when we optimize signal timing, the first step is go there to count the cars. I spend maybe 1/3 of the budget counting the volumes, counting the cars, then build a model. So the question is, do we have to always go that way? Can we have an easier way, quicker way, and maybe even better way to come up with a optimized timing plan? So the question is, can we optimize signal timing without the traffic volume counts? Whenever I ask this question, I always get two different responses. Some people say, yes, definitely we need to count the cars. And some people say, no, you don't have to do that. I think for any agencies who have been doing signal timing in-house, you probably rarely count all the turning volumes for all the intersections. But I know for firms, consulting firms, they are not really familiar with the system. Then the first step usually is to count the cars. What I want to emphasize here is that, for doing signal timing, what we really need is not the traffic volume. What we really need is what cycle length do we need, and how to come up with a phase timing, right? So volume, geometry, those kind of things are just interim variables to get you there. So if we can get the cycle, we can get the split, then of course you don't have to always count the cars. Then if you look at our signal timing work, I would say more than 80% of the cases is a retiming. Retiming means you already have some kind of timing plan running. Therefore, there already exists in cycle length and splits. Now, do we really change the cycle length often? Right? So what I would say is you probably don't want to change the cycle that often unless it's really justified, it's really necessary. Because if you change the cycle, most of our systems is on the grid. You change one arterial, the cycle length, it's going to impact the crossing arterials, right? It's going to cause a lot of issues. And also, in many cases, our cycle length is really determined based on pedestrian crossing needs. It's not really based on traffic demand. In that case, the cycle is probably already determined, the minimum cycle to run to accommodate the pedestrians. Therefore, that's another reason, you don't have to always change the cycle length. So if we don't change the cycle length, that means most of the existing phase splits are already good. If it's not good, so people probably have already called you. There's a long queue there. It's not clearing. The green is too short, right? So you probably have already made the adjustments. And plus, all our modern controllers have this feature to be able to log the history of phase splits, right? You may have heard about this ATSPM, Automated Traffic Signal Performance Measures. Right now is promoted by the FHWA. So these kind of systems do have a function. It's called a split monitor. You can look at a history of the phase splits. In this case, I'm just picking one intersection in Las Vegas and this westbound left turn phase 3. Each timing plan, each timing plan, they will tell you what is the average split and how many times it's forced off. Forced off means you reach the max. How many times it's gapped out? Gapped out means, you really didn't reach the full split. So whatever you provided in your timing, 67% of the cases gapped out. That means you can still squeeze, some time from this phase. For other movements, the same thing. And even without ATSPM, without such automated system, the controllers, the modern controllers, all have this capability. I'm just showing you one here. It's from a controller. The logged information shows which pattern, which is a timing plan, and the cycle length is running. And also G means gapped out, which phase gapped out. If you get a lot of gapped out, so that means the time is kind of excessive. So you can certainly reduce the time from those phases. So we actually, the time work we do here in the region, we rely on this kind of a phase split history a lot to kind of come up with the cycle and the phase split, right? So that's the optimization part. The point is, without volume, without counting the volume, you can still do a lot of coordination work. So third part, third aspect is about timing diagnosis. I'm actually spent quite a bit of time here talking about this issue. Diagnosis. Why timing diagnosis is important? Why timing, could go wrong? So these are the main reasons. The speed. You design the timing based on assumed speed, right? In reality, the speed can be different because of the traffic volume, because of the mid-block pedestrian crossing, because of the turning vehicles. It could all affect your speed. Therefore, your actual driving may not match what your timing plan. Because most of our signals are running coordinated, actuated. Actuated means, the side street, if the demand is low, right, it can gap out. When it gapped out, then the green will return to the main street early. So how do you know when you are in the field driving the arterial, how do you know it's an early return? you can only guess, right? If you are really experienced, you hold a time-space diagram, well, this might be early return, but you are not sure. So you need to know if it's indeed an early return or something else, a transition, for example. Early return is normal. It doesn't mean anything is wrong, but you just need to know that. Offset. Offset is one of the most important parameters for coordination. You would think offset is a simple concept, but I found out most mistakes made is actually related to a wrong offset reference. So in this case, I'm just showing a quick example. It's the same timing information. There are two different ways of referencing offset. The first is called TS2 first green. If you reference TS2 first green, which is here, that offset is 40. If you reference begin green, the coordinate phases 4 and 8 is actually here, so 6, 6. So I found out actually a lot of people make mistakes in regards this kind of offset reference. So if you actually program the wrong offset, so obviously your timing will not run correctly. So you need to find this out quickly. A very common situation is signal out of coordination. Because of preemption by emergency vehicles, sometimes pedestrian crossing could also cause this kind of signal out of coordination. Lost communication. So due to construction, you just cut the wire, so there's no communication. So when the signal is out of coordination, of course, the timing will not run correctly. Finally, the clock time. So you'll be surprised how many times actually the clock in the controllers can go wrong. Okay, you would think with the communication technologies now with the central system, so the clock should be very accurate. But I have found so many cases, the clock actually can go wrong. So all of these, right, could cause your timing to run not according to what you intended to. So how do we quickly, identify these issues? That's the diagnosis part. But I know in the audience, not everybody is familiar with the signal coordination, right? So I know some of you maybe, I don't have to repeat all of these, but for those who are not really familiar with the signal coordination, I just want to quickly explain, how to really understand the signal coordination. The key parameters, cycle, split, offset, sequence, phasing sequence, these are the parameters, right? So the non-coordinate phase means side street or main street left turn, right? They can gap out or can be even skipped if there's no demand due to a lack of demand. So you need to understand that doesn't mean anything is wrong. It's just normal situation. So therefore, green return to the main street is normal. It doesn't mean anything is wrong. How do we know if the coordination is not running correctly? So this is one thing you need to know. Coordinated phases, which usually is the main street through phase, it cannot turn later. Okay, if your timing plan designed that way, it cannot turn later. Okay, but to whatever you design in your timing, nor it can terminate earlier. So the main street usually hold to the max. So if you found, actually ended earlier, so that is the indication something might be wrong. Okay, so you really need to know this rule. And this is how to judge if the timing is running correctly or not. So using vehicle trajectory and plot on a time-space diagram is a good way of doing the diagnosis. But here I want to explain the time-space diagram a little bit. So you can see here is a time-space diagram. We have the green band for both directions in two different colors, right? I'm just using this first example, first intersection as an example. So how do you read the colors, right? This is a phase 2, 5, So the green color, which is going from top to the bottom, we can say going southbound, right? So that's phase 5, that's phase 2. And then the blue is going to the north, which is phase 1 and phase 6. And its actual timing is just like this. If you have used the synchro, so you're probably very familiar with this. So to put it on a time space diagram, so you know these are the left turns, the different color represents the 2 directions. So yeah, I just want you to understand these basics, how to read a time space diagram, because next I'm going to show you, some diagnosis examples. Right. So this is one case, right? You look at the time space diagram, it's very good timing, very good bandwidth. Then you look at, these are the vehicle trajectories, right? These are the vehicle trajectories. If you look at it, actually there are quite a few stops. So why is that? I explained, right? Here is green, but why you stopped on green? So this is an indication something is wrong with this part of the system. You look at the stops all because of you stopped on the green, which is you shouldn't. You should go through, right? So in reality, that is actually red. So because of that stop causing another stop there. So this is just purely by trajectory. Here I'm showing you another example, right? I have 4 trajectories here, 1, 2, 3, 4. So which one, just a quick test, which one do you think that could be wrong, that is not matching the timing plan, right? Obviously, I couldn't hear, I couldn't have anybody to try to answer this. But some people may say, here, why did you run the red, right? So in fact, nothing wrong with this. Earlier, I explained the red is on the side street, but the side street doesn't have to go to the full split. If there's no demand, it just gap it out, right? So nothing is wrong with that. But if you look at this trajectory number 4, okay, this is a clear indication something is wrong, right? The blue, which is supposed to be green, but the vehicle stopped when it's supposed to be green. To show you what's happening, see, it's supposed to be green, but in fact, it's red. So this is an indication of something went wrong with the signal. So this is a transition. A transition happened, but the preemption vehicle already gone by the time the car reached here. Okay. So next, I'm going to actually show this same example. This is a mobile tool, we can use to do this kind of I want to turn the audio off. So this is a time space diagram. Here's the video. It's all synced together. You can see it's running toward the yellow, so turned yellow. So this matched very well, right? And the next signal, so we are in the green band, right? Pass through that one, no problem. Okay, now look at this one. This counting down shows the green is supposed to last for another 38 seconds. And I told you, this is the coordinate phase. It shouldn't terminate earlier, but now you see it just turned red. So you immediately know something is wrong with the signal. Then you have to find out, is that a wrong offset? Is that a transition? If it's transition, so it doesn't mean anything wrong with your timing plan, right? You just need to wait until the transition is over. Well, here is another, I think, a good example of this kind of a mobile application. This video created by Andrew Jankura at RTC here. So I just want to share this with you. On this video, you can see this is the central system, ATMS. This is the mobile app. Now, this is the field operations. So whatever the field runs should always match the central system, right? But the timing plan on the app is the timing is supposed to run. So if you see they do not match, then you know probably something went wrong. So I'm just going to play this video. Everything is in sync. You look at it here, the status is in sync. Now it's on the side street, phase 8. Phase 8 just terminated. Main Street started. 2 and 6, which is north-south direction. Now you see the northbound, which is phase 2, it will end first. Yellow, that ends. You see all these matched pretty well. Now southbound left turn and through are going. So it's about to end. Now it's just ended. So turn to the side street, right? So everything matched when it's in sync. Now the next example is when the signal actually has a transition. Now you see, now it's in transition. Long means in transition. According to the timing plan, phase 1 and 6, southbound should be green, but it's not. Right? The side street is actually running. So ATMS reflects what's in the field, but doesn't match this app. So we know something is wrong. So we know this is a transition. You just wait until the transition is over. So it's reducing the time difference, right? So 8 seconds still difference. You can see still won't match. You see that terminated a little bit earlier than the app. Okay, now the transition is over. Okay, then it should match. So Main Street ended and then side street start, right? So this is a illustration of this kind of mobile applications to diagnose signal timing errors, right? But there are some other apps you may have heard. One is called Enlighten by Connected Signals. The other is All These Traffic Light Information by TTS, a company. So I have 2 YouTube videos, so there's no time for me to play those videos. What I want to say is that those apps were developed supposed to help drivers to know how many seconds left on the green or red, so to reduce drivers' frustration. I don't know how much is really used for signal timing, but I did find a good use of one of their tools. So this is the real-time signal timing status display they publish on the website. So they gave me access to their website. Instead of checking against the central system, I actually, before go to the field, I check against their website. I know this is what's really running in the field. Again, I have a video on YouTube also. So I don't, there's no time for me to play these kind of videos. So you can go back to watch how we can use these kind of tools, right? So the fourth aspect is about evaluation. How do we evaluate if the timing has done well? If you have done a signal retiming. The current practice we do before after travel runs. We compare if we really improved the timing compared to before. But these kind of before after studies, the problem is it cannot tell if there's still room to improve. You don't know whether we can still do better, right? So the only place I found, the only agency that has something which is called the Corridor Synchronization Performance Index, CSPI. It's a score based, on speed, number of stops, and stop per mile. So these are the performance measures usually we collect when we do before-after studies. But based on that, they actually come up with an index to tell you what score you achieved so that you know if you have done the best or there's still room to improve, okay? And also the Purdue system, which is in the ATSPM, they provide some performance measurement, but you understand that that is just based on one specific link, doesn't really reflect the corridor level, okay? Unlike the travel time run. So travel time run, as I believe, still is necessary. And at UNR here, we also developed a framework, something similar to Orange County's performance index. So these are the things I want to kind of show you. This is Orange County's. So based on speed, based on green per red, this is really the stop per mile. So each one you get a score, right? These are the speed, and then these are the corresponding scores, stop corresponding scores, right? Based on that, and then you classify the corridors by tiers. For example, if you achieved 80 above, so that's very good progression. There's no need to do signal retiming. On the other hand, if it's less than 50, then it's pretty bad. You may need to look at the signal timing. And I just want to use a case study to show you how this kind of a performance index looks like. So this is in Caltrans District 8, a case study that I actually did. 10 signals. This is the before timing, right? Before time space diagram. You can tell this is going eastbound, the green, the blue is going westbound. So eastbound is a little bit better than going westbound. Westbound, basically there's no bandwidth. These are the vehicle trajectories, collected. You lay on top of the time space diagram. And based on that, this is the Orange County's performance index. Each run, you get a score, you get an average. So for example, this is the before case, you get 59. So 59 is slightly above 50. 50, below 50 is bad, right? So 59, not so good. And this is UNR's. So this is something we developed. It's sort of an enhancement of their performance index. Instead of a score, which is not even based on 100 scale, so we gave you a letter grade. I call it a qualitative signal timing, right? So this is the bidirection and average. You can see westbound, you get a D. Eastbound, you get a B+. And I told you the eastbound looks a little bit better, right? This is kind of a confirmation based on the actual travel runs. Now this is the after. After, by looking at the trajectory, you can see it's all pretty good, except for this one. So this one, you may tell, in fact, is during a transition. So the signal is supposed to be green, but we stopped when it's green, right? So even with this, we achieved, this is Orange County. You can see Orange County can be above 100, the score. The highest, I think, is 107. So 99, above 80, which is excellent. This is UNR's, now it's all A minus. A minus eastbound because of that preemption. If you exclude that run, which is during transition, then it should be quality service of A, okay? Now, these kind of trajectories, if you manually go to do travel runs, it's going to take a lot of time consuming, right? But how can we get, these trajectories automatically? So there are, in fact, there are a lot of resources where we can get these. I don't know whether you heard about Metropia, this company. So they have this app. So they developed this app to encourage people to travel during off-peak hours. Select uncongested road. Now don't always go on the freeway. So they encourage people to travel, change their travel pattern. So by using this app, they gave you an incentive, You may accumulate points and then exchange some gift card. So therefore, they gather their trajectories, their origin destination for transportation purposes. So these are the trajectories actually they provided for me just to show, indeed, actually the quality of the trajectories are really good. We have, there are many other companies. There are Inrix, there's, Google, Uber, they all have this kind of trajectories. But I'm not very, so far it has not been successful for me to really get their trajectories. But I happen to know another companies, similar companies called Taikon. So I asked them, can you provide me some trajectory data? So here I'm showing you, this is the one that we collected manually in the field by driving the arterial. You can see the resolution is pretty high. So every data point, every 1 second we get one location data point. This is from the Taikon's trajectory. So roughly about 3 to 5 seconds per location, but it's still pretty good. As you can see, right? I think it's good enough just for evaluating signal timing purposes. So far, this is the best trajectory I have seen from a data service company. And here I have kind of animated this trajectory. You can see about every 3 seconds, you move one location, right? This is the arterial in Carson City and Nevada here. So if we can, automatically get these kinds of trajectories, you get a much larger samples. You don't have to spend a lot of time to do these kind of travel runs in the field. Of course, you can also look at the Google map. So this is in Reno. We did a retiming for this McCarran Boulevard. That was before, that was after. So just pick a weekday, Wednesday, Tuesday, look at it before, look at it after, so you can even see the improvement. Of course, it doesn't have the details, right? But to summarize, these are the key things that I talked about. I emphasized these 4 critical aspects: the mode, so managing data, optimizing when the minimum data, diagnosing, and evaluating signal quality. So showed you some technology tools that can help you on the signal timing work, right? So basically, I showed you a mobile application, ATSPM, connected signals, crowdsourcing, and Metropia and Taikon. Of course, other companies also have the potential. Well, before we go to the Q&A, I want to do a little advertisement here. So in LinkedIn, I created this Global Traffic Signal Control Forum. So welcome everybody to join this forum. Occasionally we post, questions, discussions, videos, mainly focusing on traffic signal control. Okay. There's another thing that's kind of my toy in my lab. I have a video on YouTube. I'm not going to play it now. So this is really a good facility for students, for researchers, just to do signal timing, do research, learn signal timing in the lab. We have an interface to design the signal timing plan. Automatically, you can get the timing plan into the real controllers, get those real controllers, and then you run the controller with the vSIM simulation. So whatever you see on the vSIM simulation is controlled by the real controllers. And we also have this physical model. You can actually demonstrate by using this kind of a model, the signalize and the small car, to demonstrate the good timing, bad timing. So that is a toy in my facility, in my lab. So when you have a chance of visiting Reno, make sure you let me know if you want to see this. I will give you a demonstration. The final slide, just to highlight some of our research, and basically, this is how I'm teaching, showing the students in the field how signal timing work. So they are now all graduated. So this is Andrew. Right now he is actually the project manager at RTC here, so leading a group of my students to do the signal retiming work. With that, I think that's all I want to talk about it. Hopefully I'm within the time frame, and I guess the next is questions, Q&A. What is the best practice when it comes to retiming signals corridor within city? Is it 30% per year for entire city must be retimed? I guess, you know, this is all depends. So one third of the signal, every year you retime 1/3 of the signal. So basically every 3 years you go a full round. So that's the recommended practice. That, in fact, that is how we are doing here in Reno. So we every year we retime 1/3 of them. So by the end of 3 years, we retime all of them. Then the new cycle starts again. What is the best practice? Okay. The sequence, I should actually go from the bottom, right? Is the car trajectory information freely available, or is there a cost? Yeah, definitely there's a cost. So this company, Taikon, you know, they provide this kind of data, but it's not free. They actually purchase the data from some other places, then they process the data so that you can at least display and read. How do you plot the trajectory on the time-space diagram? Well, this is the app I talked, right? Yeah, there's an app. You can search on the Apple Store. It's called TransSync-M. So you code the timing in the app. You go to the field, and automatically the GPS is plotted on the time-space diagram. You can also record the video. What is the best practice? We already answered that. What is the best way to learn signal timing when you have little previous experience? Can you recommend a specific book, course, or program? Okay. In terms of reference material, signal timing manual, I guess is probably the best reference material, but you probably don't also want to read the whole signal timing manual, right? If you ask me, you know, what's the best way? Yes, you need a good tool to help you to best understand how signal timing work. Then to know how to easily develop optimized timing plans, right? So the tool I showed you, those like particularly the mobile tool, is really expedite your learning curve, your learning process. Again, join the LinkedIn group, or you can also watch my YouTube channel. I post a lot of these kind of videos. So particularly the LinkedIn, so those are mostly educational. I explain how the time-space, what is time-space diagram, how the time-space diagram works, and you know, how to know when there's a timing error, those kind of things. Okay, join the group. How many signals to be retimed every 3 years in your Reno network? We have about 400 signals here. Okay, 300 of them are coordinated. So we retime about 100 every year. Would you consider the Weizhou data similar to Taikon? Actually, I don't know. I'm not familiar with this Weizhou, what it is. Taikon is a company just like Straight Light, Inrix, but Taikon, their trajectory is as far as I know, is the best I have seen so far. I talked to Inrix, but Inrix is all aggregated. I tried to request some high resolution trajectory data, but I was not able to get any from Inrix.